This figure shows the TLS handshake protocol communication that occur between client and server. Uh, TLS handshake protocol is used to establish the cryptographic parameters between both client and server that are going to be used to establish different connection between them. So the overall architecture of this protocol is shown over here in this figure. First, as you know that TLS work on top of TCP, so client and server need to establish with each other a connection through TCP handshake. So as we know that TCP handshake consists of three messages, that is sync will send from client will reply with sync ACK, and server will reply with sync ACK, and client will then send back ACK message. Okay, so once client send ACK message, along with this ACK message client also send a message called client hello, which initiates the connection TLS session. When received by the server this client hello message, server will reply with server hello certificate, and server hello will be done. Okay, so server will send two messages as a response of client hello. Okay, and then when client receive the server hello and certificates from the server, then client will have to send the client key exchange. Okay, first message client key exchange, and second message that client is going to send is change cipher spec protocol, because until this time the session has not yet established. Session will be established when client is going to send this change cipher spec message. You know, change cipher spec is another protocol in TLS which consists of only one byte, like you know we have discussed it over here. Yes, this one, change cipher spec protocol. So in handshake, once client send its key exchange messages, after that client send one byte of this change cipher spec protocol, and the purpose of this change cipher spec message or protocol is to change the state of your connection to the to finalize this session, not a connection but session, because it will cause the pending state to be copied into the current state. Until here the state is pending. So client will send change cipher spec message and server will respond with its own change cipher spec message, and then a TLS session is established between both parties. Now we will go into little bit detail of these messages, what is there in client hello, server hello. Okay, in the book they also show that this communication between client and server can be viewed as having a four phases. Phase 1, where both parties send hello to each other, client send hello, server responds with its hello, and then server send these messages where it's certificate, server key exchange, server certificate request, and hello done, because you know we have already shown over here the message types and what are the contents or parameter in these messages. And then client will send its own certificate key information, and then after phase 3 and phase 4 client send change cipher spec and finish message, and server will send its side change cipher spec and finish, and after that handshake protocol finished and a session has been established between client and server, and now they can establish connections on that session. Okay, so let's go for it. So as we know that between, if this is a client, this is server, first message is client hello. So how client hello look like? In client hello message, client will inform to the server the protocol version he is running, which TLS protocol version the client is running, and the cryptographic algorithm that client supports. If you look at the detailed structure of this client hello message, this client hello message is having this structure. Okay, this is a structure, and this structure have client version, which client has to inform to the server the highest version of the TLS protocol supported by the client. As per 2018, the highest version of TLS protocol that is available is TLS 1.3. So client will have to inform about its capability to the server, that which highest version of the TLS protocol I am supported, it has to inform to the server. Then a random number that is chosen by the client, and session ID if the client wants to resume an old session, but if it is a new session then there will be null, session ID will be null. And cipher suite, which gives information to the server about the cryptographic algorithm that are supported by the client. Like client can tells to the server, I can support RSA or Diffie-Hellman or DES or AES, SHA 256 or whatever. And then compression method, if compression wants to be used on this connection, then which compression method is supported by the client. So this is what a client hello message contents look like. Okay, now after this client hello, okay, this is client hello message. Okay, and client server hello is, now server hello is what? Server respond with highest protocol version both client and server support. It is possible that client supported right now the highest version of TLS, that is 1.2, and server has a support of 1.1, 1.2, 1.3. So the highest version that is being supported by both of them is 1.2. So server has to inform to the client, or they have to agree on which version of TLS they are going to use. And then server will choose about from the cryptographic suite that is sent by client the strongest cryptographic algorithm, and then inform to the client that okay, you are supporting RSA, Diffie-Hellman, AES, DS, okay, we will use RSA and AES on this, let's suppose. So this is how or the contents of, you can say, the server hello message are, which is version, the version from server on which both client and server will agree on and work with, cryptographic suite that is chosen by the server, which cryptographic algorithm is being used by the server, server side random number, okay, NS will be the random number, and server key exchange message, which tells that it will going to use which algorithm and key exchange related material. Okay, in the coming slide there are some notation that are being used to represent these messages structure. Like if it is something like this, mk mean message m is encrypted with key k, and signature of on m using key k, or hash of message m. So if we come back over here, so now client, the third message or the third transfer between client and server is about, now client has to send, now we enter into phase 3, because client hello done, server hello done, server has sent its information about signature and all other to the client, and now client key exchange need to be initiated. So if you look at here, what are the actual contents of the message that are being sent by the server are version, suite, random number, and signature on S, key of S through CA. CA is the certification authority. So it's sign S and KS using certification authority public private key. It is what? It is the public key of server, which is signed by certification authority, because as you know that, or you can say public key certificate, we already discussed, this is public key certificate that is being sent by server to client, that this is my public key certificate, where server is going to inform to the client about its public key, and public key need to be issued by the certification authority, so that we make sure that this public key actually belong to this server. It is just a surety. So for to giving this surety, certification authority will sign this public key with its private key, so that client can verify it. Okay, and server hello done. Okay, what is in the client key exchange? In the client key exchange, client generates some secret key material and send it to the server encrypted with the server public key. The server public key, that the one that is sent by server from in this message. Okay, this ks is the server public key. So here client will generate a secret key that is being used on this session. Okay, we call it secret C, secret of the client, and encrypt it with the public key of the server, and server can get this key by decrypting this message with its private key. So if everything goes well, if all things are normal, client and server will share some secret key material, that is secret C at this point. This a common secret key is being shared between client and server at this point, and both party will switch to key derived from secret C, and then this secret C will be used to derive another key, and both party will switch to use that secret key. Now we after performing this key exchange, then there is need to perform the creation of shared master secret. So what is a shared master secret? It is a one-time 48-bit value that is generated for the session by mean of secure key exchange, and we have seen this is the secure key exchange that is being finished over here, where both parties share now this secret C. Now this secret C, we call it a pre-master secret, because the creation of shared master secret is completed in two steps or two stages. First, a pre-master secret is exchanged between client and server. So this is pre-master secret, okay, which is sent by client to server encrypted with the server public key if the underlying algorithm that is being chosen by server is RSA. We will discuss it in coming slide. And then from this pre-master secret, a master secret is calculated by both parties. So this pre-master secret exchange has two options. You can either have RSA. If server choose RSA for key exchange, then both parties will share this key by a 48-bit pre-master secret is generated by the client, like here. This pre-master secret is generated by the client and sent to the server encrypting with the server public key, okay. So this is one way to share the pre-master secret. But if server choose here in this cryptographic suite Diffie-Hellman as a key exchange, Diffie-Hellman algorithm as a key exchange, then the thing is both client and server will generate Diffie-Hellman public key, and after these are exchanged, each side perform the Diffie-Hellman calculation to create the shared pre-master secret. So now I will explain to you this thing. Okay, Diffie-Hellman key exchange is the first published public key algorithm, and this algorithm is only used to share a key between the parties. You cannot use it for encryption or decryption purpose. It only provides you key exchange service, and there are a number of commercial products which use this key exchange technique. The purpose of this Diffie-Hellman key exchange protocol is that two users will securely exchange a key that can be used for further communication between them by using symmetric encryption. And the algorithm itself is limited to the exchange of secret value, and it is the difficulty of this algorithm depend on computing discrete logarithm problem. Like the RSA difficulty depends on factoring the large number. So Diffie-Hellman key exchange algorithm difficulty depend on the computing discrete logarithm problem. This is the overall messages that are exchanged between two parties when they want to share key through Diffie-Hellman protocol. If like Alice and Bob want to share a key with each other using Diffie-Hellman, then first of all Alice and Bob have to share a prime number q and another number that is called alpha, such that there is need to satisfy alpha two properties. One is alpha should be less than q, and the second is alpha is a primitive root of q, and this q and alpha is a public key. These are public values, they don't need to keep them secret, but Alice and Bob must have to use same q and same alpha value, so they have to agree on these public parameters with each other first. Then Alice will generate a private key, and this private key we call it XA, private key of Alice. such that this XA should be less than Q. And Bob will also generate his own private key, and we call it XB, and condition is it can be any random number less than Q. XB should be less than Q. Then Alice will calculate her public key as YA. YA is will be alpha raised to the, how we will calculate YA, alpha raised to the power XA mod Q. So this is the computation, and here discrete logarithm problem is involved. And Bob will also calculate his public key in the same way, like alpha raised to the power XB mod Q. And then both parties will send their public keys to each other. Alice will send her public key YA to the Bob, and Bob will send his public key YB to the Bob. When Alice receives Bob's public key, then Alice will calculate a shared secret key between Alice and Bob like this: YB raised to the power XA mod Q. And Bob will calculate the shared secret key as YA raised to the power XB mod Q. Okay, now we can see that how both parties share. How can this K is same as the one that Bob calculate. You know YB is equals to what? Alpha raised to the power XB. So YB is alpha raised to the power XB raised to the power XA. So our key here is equals to this value. This is what Alice calculate, shared secret. And this is same what Bob calculate. If you look, YA, what is YA? YA is alpha raised to the power XA. And then Bob do what? This is YA, and Bob make what? Raised to the power XB. So both parties, Alice and Bob, now share a secret key K that is same, alpha raised to the power XB XA or alpha raised to the power XA XB. Both these K's are same, which is being shared between Alice and Bob without sharing any secret in the start. They don't have any secret in the start. This Q is public, alpha is public. Okay, this keys YA and YB are also public. But by using all these public parameters, they come up with this shared secret key K with each other. The other party who is going to see this YA and YB, they cannot get this key from these public parameters, because in order to generate, like if somebody get YA, it is what? Alpha raised to the power XA, and another party if they get YB, it is alpha raised to the power XB. And if they are going to do something like this, YA multiplied by YB, it will be what? YA alpha raised to the power XA, and multiply alpha raised to the power XB. When bases same, power add, alpha raised to the power XA plus XB. So they cannot generate this alpha raised to the power XA into XB. If they get this YA and YB and they just multiply them together, they will get alpha raised to the power XA plus XB. So no, they won't be, they can generate this key only if from YA or YB they are able to get XA or XB. So in order to get XA and XB from the power, they have to solve discrete logarithm problem. So in order to get XA or XB from YA or YB, like from here, if somebody wants to get XA or XB, like from YA, if you are going to get XA, what you have to do is XA will be equals to log to the base alpha of YA. Okay, they know alpha, they know YA, so they just have to calculate log to the base alpha YA mod Q. This mod Q will make this problem very difficult to solve. This is not a normal logarithm. It is discrete logarithm problem where this mod operation will make for attacker to get xa or xb out of yb very difficult to get. So this is a very first proposed public key algorithm that is based on discrete logarithm problem. And it can be used in TLS algorithm for key exchange. So for key exchange we have two options, either RSA or Diffie-Hellman. So if it is Diffie-Hellman, then your pre-shared master secret is derived by using this protocol. Here in this slide shows that there is one problem with Diffie-Hellman key exchange, is that which is called man in the middle attack. So this shows the man in the middle attack, like Alice when generate her public key YA and send it to Bob, man in the middle Darth just receive this YA and he send, instead of this YA, he generate his own two private keys XD1, XD2 and two public key YD1, YD2 as same alpha that is being used by Alice and Bob, and Q that is alpha raised to the power XD1 mod Q and YD2 as alpha raised to the power XD2 mod Q. And now what Darth did, instead of sending to Bob Alice public key, he will just keep this public key with himself and send his own public key to Bob, which is YD1. Okay, there is no way for Bob to confirm that this YD1 that he received actually come from Alice or Darth. There is no user authentication or MAC is with this public parameter. So when Bob received this public key, he will assume that this public key from the Alice, and he will generate his own public key and send it to Alice, and the man in the middle will receive this public key and stop it, and instead of it Darth will send YD2 to the Alice. Now Alice will assume that this YD2 is Bob public key, although it is from Darth. So now Darth send two public key that he generate by himself to Alice and Bob instead of their own public key. Now when Alice will receive YD2, what she will do to generate sheer secret key, she will do whatever it receive, assuming it is Bob public key raised to the power her own private key mod Q. And same when Bob will receive YD1, he will generate this K1 as this public key that it receive YD1 raised to the power XB mod Q. And Darth can generate both K1 and K2. Why? Because Darth know YA, so he can generate raised to the power XD2 to get K2, because this is K2. K2 is what? These K2, Darth can generate both K1 and K2. Alice and Bob share two different keys, not the same, but the different one. Like if I will, what is YD2? YD2 is what? Alpha raised to the power XD1 raised to the power XA. This is K2. Okay, and what is K1? K1 is YD1. What is YD1? Alpha raised to the power, okay, this is D2. So alpha raised to the power XD2. This is D2. And here what is YD1? Alpha raised to the power XD1 raised to the power XB. Now this x raised to the power d2 xa and this x alpha raised to the power xd1 xb. So k2 and k1, they are not same secret key. They do not share same secret key. They actually share the key with Darth, that is a man in the middle, and Darth can generate both k2 and k1 because he has ya, that is the public key of the Alice, and xd2, that is his own private key. So ya, we know what is ya. Ya is alpha raised to the power xa, and he can generate or power it to xd1. So this way alpha raised to the power xa xd1, uh, he can okay, xd2, not xd1, sorry, xd2. So he generate alpha raised to the power xd2 xa, alpha raised to the power xa xd2, that is k2. So Darth can calculate k2, and Darth can also calculate k1, where yb, what is yb? Now yb is alpha raised to the power xb raised to the power xd1. Okay, so Darth can calculate both the shared secret keys of Alice and Bob. So Alice and Bob now agree on two different keys. They actually share a key with Darth, not with each other. And whatever Bob now will send to Alice, he will encrypt it with K1, and Darth no K1. Darth can decrypt it and re-encrypt it with K2 and send to Alice, and Alice will encrypt things with K2. Darth can decrypt it and re-encrypt with K1 and send to Bob. So this way, man in the middle can see all the communication occurring between Alice and Bob. Once pre-master secret is shared between client and server, then they can go for the next step to generate the master secret, which is 48 byte length a key. And this is how we can generate this 48 byte master secret. PRF stands for pseudo random function. To this pseudo random function, we give as input our pre-master secret, which is being shared between client and server during key exchange, and then a string master secret. Okay, this is a string that we write as it is. Then a random number, that is client hello random and server hello random. If you remember here, when we perform this, NC is the client hello random number and NS is the server hello random number. So these random numbers which are shared between client and server during hello message, that also are concatenated over here in this pseudo random function input. And then through this pseudo random function we generate a master secret. Okay, so now master secret has been generated. From this master secret, now we are going to generate 4 keys. Okay, because after key exchange we need to run change cipherspec protocol messages between client and server to finish the session establishment, or to make the session state to active state. So change cipherspec require a client write MAC secret, the key that is used by client to calculate MAC, a key that is used by server to calculate MAC, a key that client will be used to encrypt the messages, and the key that server is using to encrypt the messages. And if they require initialization vector, then client write initialization vector and server write initialization vector. So these all 6 key values are generated from the master secret that is being generated over here from pre-master secret. First pre-master secret is generated, from pre-master secret master secret is generated, and then from master secret these 6 keys are generated. So here we show that how we generate pre-master secret. Pre-master secret or pre-master key is generated by using either Diffie-Hellman or RSA algorithm. And then from pre-master secret we generate 48 byte master key, and then from 48 byte master key we generate these 4 keys that are being used for calculating the MAC and encrypting the messages. So here we show that how we generate these 4 keys from master secret. This is how we calculate master secret, as I already described in the previous slide. And here it shows how we are going to generate the key block. This key block has a length depending on how much length for each key required. okay, like let's suppose for mac calculation our key is of 100 byte 100 byte 100 byte 100 byte, so this key block will be of 400 byte. Okay, how we calculate this key block? We use a special hashing function md5, and to this function we give these values as input. Okay, master secret, obviously master secret is used to calculate this key block, so master secret concatenated with, and here we are calling sha function. To sha function we give a string, this string a, concatenated with again master secret, concatenated with server random number, client random number, then again concatenated, here we call again md5 function, and to md5 function we are giving master secret, then here we call again sha function, and then string is changed from a to b and all. If we look here, you know, this is all the diagram which show the calculation of this key block by repeatedly calling these hash algorithms which are md5 and sha1 one by one, and we call it hmac. In that case this hmac will be md5 one time and then sha1, and this secret is what? Your master secret. Then we will discuss heartbeat protocol, TLS. All protocols has been discussed until now, so now the next protocol is heartbeat protocol. If we look in the context of computer network, then we can say that what is a heartbeat? Heartbeat is a signal which is sent periodically after every particular time. This periodic signal is generated by hardware or software to show that everything is normal, or to synchronize both parties with each other. Heartbeat protocol in TLS is used to monitor the availability of protocol entity. Like if we look at the specific case of TLS, so heartbeat protocol is defined in this RFC number 6250 in 2012, and this RFC defined two things or two protocol. One is TLS, another one is DTLS, datagram transport layer security, because TLS work on top of TCP, and DTLS is the protocol that that work on top of UDP. Heartbeat protocol run on the top of TLS record protocol on the application layer. If you look at the protocol stack, if we look at our protocol stack, where is our heartbeat protocol? We have discussed it in the start. This is our heartbeat protocol. Heartbeat protocol work on top of TLS record protocol in application layer. This is our application layer. Further, heartbeat protocol consists of two type of messages. One is heartbeat request message, and the other one is heartbeat response message. And the use of handshake protocol is established during phase 1 of the handshake protocol. Yani we use this heartbeat protocol in phase 1 of handshake protocol. What is the phase 1 of handshake protocol? We have to refer back here to this slide. This is phase 1, where client and server both perform hello with each other, client hello and server hello. So here we use heartbeat protocol, where both parties, client and server, will show whether they support heartbeat protocol or not. And if heartbeat protocol is being supported, then the peer indicate whether it is willing to receive heartbeat request and respond with heartbeat response message only, or willing to send heartbeat request messages. Heartbeat request message can be sent at any time. Whenever a request message is received, it should be answered promptly at the same time, immediately, with a corresponding heartbeat response message. And heartbeat request message, if we look, yeah, it consists of some fields. What are the fields in heartbeat request message? Heartbeat request message consists of payload length, payload and padding field. Okay, we will not go into the detail of the structure of heartbeat protocol, but the purpose of heartbeat protocol we need to discuss. And what is the purpose of heartbeat protocol? The first purpose is it make it assure that sender uh, uh, that is that the it make it sure the sender that the recipient is still alive, even though there may not have been any activity over the connection for some time, but it just try to make sure the other party is active, is alive. Okay. And second purpose of heartbeat protocol is that it generate activity across the connection during idle period. When there is no communication, it generate activity on that connection. So this activity will avoid the closure by a firewall of this connection, because firewall, if the connection remain idle for some time, it will be closed. So heartbeat protocol will just generate some activity on that connection, so that firewall will not close this connection, considering it as a idle connection. The requirement for the exchange of payload was designed into the heartbeat protocol to support its use in connectionless version of TLS. What is the connectionless version of TLS? DTLS, which work on the top of UDP. TLS work on top of TCP, and DTLS work on top of UDP, connectionless TLS. We also called it connectionless TLS. So heartbeat also play a role in DTLS, because a connectionless, okay, what is the role of heartbeat in a connectionless service? As we know that if there is a connectionless service, it is subjected to packet loss. So the payload enable the requester to match response message to request message. So the same version of heartbeat protocol is used with both TLS and DTLS. So payload is, so heartbeat payload is required for both TLS as well as DTLS. Initially, the protocol that was proposed in 1994, it was called SSL, but later on it has been, when become standardized, its name changed to TLS. And there were many vulnerabilities or weaknesses was there in SSL, which has been removed in TLS. The type of attacks that are possible on SSL was, we can group them in 4 general categories. Like there were attacks possible on handshake protocol, record and application data protocol, on the PKI infrastructure, and we can say that there are some other attacks as well. And if we look at the history of attacks and countermeasures for SSL and TLS, it shows that for a perfect protocol and a perfect implementation strategy are never achieved. There is always some loopholes, some weaknesses, and attacks are possible on the security protocol. Nothing is perfectly secure. But whenever there is some attack on the protocol, we find out some weakness, and in the next version that countermeasure is applied, and a new version is proposed. So it just go through the evolution period, where it, every new version, when it evolved from the previous version, is better. Okay, the current version that is being used for TLS is TLS version 1.3, which is obviously the improvement on the previous version, and it improved the security of TLS overall. There are significant changes in TLS version 1.3 from version 1.2, and what are those changes are, like TLS version 1.3 remove a support for number of options and function, and by removing the code that implement these functions, it will no longer needed, reduces the chances of possible dangerous coding error, and it also reduces many attacks that were possible in version 1.2. So the items that are deleted in version 1.3 include compression. So version 1.3 does not support compression, and it also does not support those cipher which do not offer authenticated encryption. So you can only use cipher with authenticated encryption. Static RSA and Diffie-Hellman key exchange, 32-bit timestamp, because when a random number is generated for client hello, a 32-bit timestamp was part of that random number, so this 32-bit timestamp is removed from the client random number hello message. Renegotiation and change cipher spec protocol RC4, and use of MD5 and SHA-224 hashes with signature. So these are the options which are removed from TLS version 1.3. Another thing is TLS version 1.3 uses Diffie-Hellman or elliptic curve Diffie-Hellman for key exchange, and it does not allow to use RSA. The problem with using RSA is that if the private key of the client or server is being compromised, then all handshake using the cipher suite will be compromised. But with if we are using Diffie-Hellman or elliptic curve Diffie-Hellman, then a new key is negotiated for each handshake. Okay, so long-term private RSA key is no more being used in TLS version 1.3. So pre-master secret in version 1.3 can only be generated using either Diffie-Hellman or elliptic curve Diffie-Hellman. Okay, it also reduce the connection or session establishment phases, like it allow for one round trip time handshake, like handshake is done in one round trip time between client and server. So when client initially send it hello message, client also send its key exchange message along with its hello before a cipher suite has been negotiated between client and server. The advantage of using this is that a server can calculate key for encryption and authentication before sending even its first response to the client. So it will reduce the number of packets that are sent and received during the handshake phase, and it will speed up the process and reduce the attack possibilities. As I already told you that in 2018 TLS 1.3 was finalized after going through 28 drafts, and is now published in this RFC 8446. TLS version 1.3 has much enhanced performance and more secure as compared to the previous version, and it also removed the support for algorithm and cipher that are having any vulnerabilities theoretically or practically, like these all ciphers are no more supported in TLS version 1.3, like SHA1, RC4, DES, 3DES, AES, CBC, MD5, arbitrary Diffie-Hellman groups. Okay, here we just show the comparison of the handshake protocol between TLS version 1.2 and version 1.3. If you look at the step 1 from client to server, in version 1.2 client just send hello message, but if you look at version 1.3, client is not only sending the hello message, but there is one significant change is here, that client also send its key share for the particular key agreement protocol. So this key exchange that client has to send here in message number 3, instead of it is going to send along with client hello in message number 1 to the server. And when server receive this client hello message, the server reply with the key agreement protocol that it has chosen, and server hello message which also consists of the server key share, its certificates, as well as server finished message. So if we compare it with TLS 1.2, server finished message was sent in the 6th message here, but here in client it is just sent in 2nd message in version 1.3 from server to client. Okay, now in step 3, now the client check the server certificate, generate key as it has the key share of the server, so and send then client finished message to the server. From here onward, the encryption of the data begins by the keys that are being shared between both parties. So if we compare both TLS version 1.2 and 1.3, you can see that version 1.3 handshake saves an entire round trip, because everything is done in this round trip. Round trip means a message sent from client to server and come back. This is one round trip. In this one round trip, all information has been shared So it saves this next entire round trip in 100 of milliseconds, and a major improvement, this is a major improvement over the TLS 1.2 handshake. As I mentioned earlier that TLS version 1.3 supported authenticated encryption algorithm. So what is the authentication encrypted algorithm? Authentication encryption with associated data are those encryption algorithms which provide both confidentiality and integrity for their ciphertext. So they also support providing integrity for associated data even which is not encrypted. So this is here we show the encryption operation for authenticated encryption. So there are four inputs to authenticated encryption: key, nonce, plain text, and optional additional authentication data. This is optional. You can have it or not. We call it AAD, additional authentication data. Nonce, and this additional authentication data is passed in clear, and there are two outputs. One is the ciphertext, which is having the same length as plain text, and this tag, that is authentication tag, which is the authentication on this message which is being sent over here. And when we are going to perform decryption, then authentication decryption operation has 5 inputs: secret key, nonce, ciphertext itself, AAD, which can be of 0 length because it is optional, and then tag as well. So when we are going to perform decryption, then we have to give as input 5 things: key, nonce, ciphertext, AAD, and tag. The nonce and AAD are passed in clear, and there is one output, the plain text, which is exactly the same length as a ciphertext. If the inputs are not authentic, then function will not return plain text. Instead of it, it will return what? Fail error code. One thing that need to be considered when we are using authenticated encryption is the unique nonce. Nonce are unique for different message encrypted with the same key. Like every time if you are using same key, then nonce should not be same, it should be unique. Using the same nonce with the same key and different plain text will seriously undermine the security of this authenticated encryption. And the recommended cipher suite for TLS version 1.3 are listed over here. You can see AES 256, GC, MSHA 384, and so on. HTTPS or HTTP over SSL, or we also call it HTTP secure. What is HTTPS? It is the combination of HTTP and SSL to implement secure communication between web browser and web server. HTTPS is supported by all modern web browser, and its use depend on the web server, which whether it is supporting HTTPS communication or not, because there are some search engines which do not support HTTPS. When you look at the URL, how can you find out whether it is a secure communication or not? If you look at the URL, if it is HTTP start with HTTPS, it shows that it is secure communication, and if it is start with HTTP, it is normal communication. If we are using normal HTTP, connection uses port 80, but when we are using HTTPS, then port 443 is used, which invoke SSL service. The detail of HTTPS protocol can be found here in this RFC 2812, and there is no fundamental change in using HTTP over either you are using it on top of SSL or TLS, and both implementation are referred to as HTTPS. When you are using HTTPS, then it provide you secure communication. So when you are saying secure communication, it means communication is encrypted. So which element of the communication are encrypted? URL of the requested document is encrypted, content of the document, content of the browser form, cookies that are being sent to or from the server or browser, and contents of HTTP header. So all these elements are encrypted on HTTPS communication. As we know that HTTPS work with TLS, okay, or on top of TLS or with TLS we can say. So for HTTPS communication, the agent which act as HTTPS client, like a browser act as HTTPS client, also act as TLS client. So the browser or the client will start a connection or initiate a connection to the server on the appropriate port, and then send the TLS client hello to begin TLS handshake protocol, because to start communication with HTTPS we need the support of TLS. So first TLS handshake protocol will start, okay, and once the TLS handshake has finished, then client may then initiate first HTTP request. Then all the HTTP data that is being sent is sent as TLS application data by using TLS record protocol. The payload of TLS record protocol is then HTTP request or response message. There are three levels of awareness of a connection in HTTPS. At the HTTP level, an HTTP client requests a connection to HTTP server by sending a connection request to the next lowest layer. And typically you know that HTTP work on application layer, so the next layer is transport layer, okay, but it may also be TLS or SSL as well, because if you are having HTTP on the top, the next protocol on transport layer, if you implement TLS, then it will be TLS, but if there is no TLS, then there is TCP. So if it is TLS, then at the level of TLS, a session will be established between a TLS client and TLS server, and this session can support one or more connection at any time. So as we have seen, like a TLS request is used to establish a connection, begin with the establishment of TCP connection, because TLS work on top of TCP. So in order to establish TLS connection, first we need to establish TCP connection between the client and server. If we are looking at normal HTTP protocol, if HTTP client or server want to close a connection, this can be indicated by each party by adding a special line in the HTTP record, which is connection close in the HTTP record. And when any party, either client or server, receive this message, it shows that the connection will be closed after this record is delivered. But in case of HTTPS, because HTTPS work on top of TLS and TLS work on top of TCP, so what we have to do is, in order to close the HTTPS connection, it requires the TLS close the connection with the peer TLS entity on the remote side, which will include which will involve the closure of the TCP connection, okay. So like connection initiation, same is connection close, is in order to close HTTPS connection you have to first close TLS, and in order to close TLS we have to close the TCP connection. So what happened on the TLS level, the proper way to close the connection is that each side has to use TLS alert protocol to send close notify alert message to each other. So they must initiate this closure alert before closing a connection between client and server in TLS. So a TLS implementation may, after sending a closure alert, close the connection without waiting for the other party to send its closure alert. So it may cause incomplete close. So we have to make sure that when we are implementing this, this does may choose to reuse the session. If you want to reuse the session, then you can have incomplete close, because you can create another connection on this session. And HTTP client also must be able to cope with the situation in which the TCP connection is terminated without any prior close notify alert. If connection is closed without this close notify alert, it shows that there is some problem, or it can occur because of the programming error, or a communication error that causes the TCP connection to drop. But they said that unannounced TCP closure can be considered as the evidence of some sort of attack. So HTTP client should issue some kind of security warning when this unannounced TCP closure occurs. Secure shell. Okay, this is a cryptographic network protocol for operating network services securely over an unsecure network. The typical application of secure shell include like remote command line login and remote command execution, but you can use secure shell for any service, any network service that you want to do securely. So we can say that SSH is a protocol for secure network communication, and it is very simple and inexpensive to implement, or easy to implement. The initial version, that is SSH1, was focused on providing the facility of remote login, because this SSH1 was proposed to replace telnet service. As we know that telnet service is not secure, because in telnet service the password is sent to the other side in clear without encrypting. So SSH1, only first time when it was proposed, it provides secure remote login facility and replace telnet. But SSH also provide more general client server capabilities, and can be used for different network function, as like file transfer and email as well. The new version, that is SSH2, it fixes many security flaws in the original scheme, that was SSH1, and its RFC, or its information is here in this RFC 4251 through 4256. You can find out it. Okay, this diagram show the SSH protocol stack. SSH protocol run on top of TCP. It is not just one. SSH is not a one protocol. It consists of three protocols. Like TLS have multiple protocols, same as SSH consists of three protocols, which are SSH transport layer protocol, SSH user authentication protocol, and SSH connection protocol. Okay, the service provided by SSH transport layer protocol is server authentication, data confidentiality, and data integrity with forward secrecy. Now, what is a forward secrecy? Forward secrecy means that for a current session, if key is being compromised, the subsequent session communication will use a new key, and if somebody got the key for the current session, he will not be able to find any information from the subsequent session, because a new key will be used. And transport layer also optionally provide compression facility. Then SSH user authentication protocol authenticate the user to the server, and SSH connection protocol, it multiplexes multiple logical communication channel over a single SSH connection, and it create a tunnel kind of thing, encrypted tunnel between client and server. Okay, we start with transport layer protocol, like this first protocol of SSH, and we know that it provides server authentication, data confidentiality, and data integrity. So first we will discuss the first service authentication. Transport layer protocol provides server authentication, and this server authentication is provided based on the public private key pair that is that a server has. So it is possible that server may have multiple host keys using many different asymmetric encryption algorithm, like he has RSA public key, he has Diffie-Hellman public key, he has Al-Jamal public key. So it is possible that server has multiple host keys, or it is possible that multiple hosts may share the same host key. So both are possibilities are there. So server host key is used during key exchange to authenticate the identity of the host, because when you present your public key, server will send its public key to the client, and client need to make sure that this public key belong to this particular server. Okay, this is what server authentication. So in order to do so, there are two alternative trust models that are supported by SSH transport layer protocol. One is the client has a local database where it store each host name along with the corresponding public key. Like this is the host name and this is this public key. So when server send the public key to the client, client can search in the database the name of that server and then compare the key that received from server with the one it has stored. If both match, server has been authenticated. But the problem with this port is it require to maintain this database on the client side, which is difficult. So the alternative method, and which is more efficient method, is the host name to key association is certified by trusted certification authority. Like server will have, instead of sending its public key for authentication, server or host has to send its public key certificate, which is properly issued by trusted third party, which we call certification authority. Issue this public key certificate to the server, so server can present its public key certificate for authentication purpose. Client know the certification authority public key, and client can now verify the authenticity of the public key of server by checking the signature on the public key certificate of the server. So this is more easy way to perform server authentication. Okay, this figure show the messages that are transferred between client and server uh, in a transport layer protocol. So first the client establish a TCP connection to the server, and this is done via the TCP protocol. And you know, TCP is not the part of the so it will be done through TCP. So first TCP connection is established. Once this connection is established, then client and server exchange data with each other, and this data they are sending to each other in the form of packet inside TCP segment in order to authenticate the server and for data integrity and data confidentiality. I'm not going into the detail of these messages. Okay, this figure show the SSH transport layer protocol packet formation, where the message that you want to send on SSH connection, we call it a payload, and if the compression is being used, then this payload will be compressed and you will have a compressed payload. Compression is optional. If you want, you can use it. And then there are two fields attached with this compressed payload, which is packet length and padding length. Packet length will show the length of the packet in bytes, and padding length will store the length of the random padding field. If there is padding data is added into this payload, so padding length will be stored over here, and then you will add some padding bytes over here to make your compressed payload to the multiple of the block length. And then it will be MAC is calculated, then a MAC is calculated on it. So if message authentication has been negotiated, then this field contain the MAC value, and MAC value is computed over the complete packet plus sequence number. Sequence number is the field from TCP. Okay, and sequence number field is 32-bit packet sequence number, which is initialized to 0 for the first packet, and every time when it is incremented, new packet is generated, it is incremented by 1. So once an encryption algorithm has been negotiated, then the entire packet excluding the MAC field, not the MAC field, is encrypted after the MAC value is calculated. So first MAC value is calculated, and then this packet is encrypted, and then this encrypted message ciphertext, and then MAC is attached with it and send over the SSH connection. So you see here MAC field is excluded from the encryption. MAC is not encrypted, it is sent as it is, append with the encrypted text. Okay, here we show these three tables which gives us information about SSH transport layer cryptographic algorithm, like which algorithm are used for encryption, for MAC calculation and compression. Okay, we have already discussed how client authenticates the server. Client authenticates the server based on the public key, and then there are two methods that are being used over here. This is local database or through certification authority. So now we are going to discuss the authentication method from server, like how server authenticates the client. Server authenticates the client by using one of these three methods. First is public key method. If public key method is being used, then it depends on the public key algorithm that is chosen for authentication purpose. But in general form, we can say that clients send a message to the server which consists of the client public key, and this message is signed by the client private key. So when server receives this message, it check or it verify the signature. If signature is correct, then client is authenticated. Okay. The second method is based on the password. In this password based message, client send a message which contain a plain text password, and it is encrypted by the encryption of TLS protocol, transport layer protocol. And third method is host base. Now in host base, instead the client is encrypted, client is authenticated, instead of it host is authenticated. Host is like a machine, and this host may multiple clients are login into this host. So all the clients which log into this host will be authenticated based on the host authentication. Okay, client is not authenticated, but host is authenticated. So and host support multiple clients on it. So this method work by having the client send a signature created with the private key of the client host, and then instead of sending directly verifying user identity, the SSH server verify the identity of the host and believe that all the clients that log in into this host are authenticated as well. Okay, then SSH connection protocol work on top of SSH transport layer protocol, and when SSH transport layer protocol run, it assumes that a secure authentication connection is already in use. So on this secure authentication connection where both parties authenticated already to each other, so in connection protocol we call it as a tunnel, because connection protocol use or do what it does, it multiplexes a number of logical connection into a single connection. We call it as a tunnel. And all type of the communication which is using SSH such as terminal session are supported using separate channel. So either side may open a channel. For each channel, each side associate a unique channel number which is needed, which need not to be same on both ends. On each side they have its own unique channel number, and channels are flow controlled using a window mechanisms, and no data may be sent to a channel until a message is received to indicate that window space is available. Okay, the life of a channel, that is progresses through three stages, or there are three stages in the life of the channel. First is opening a channel, then data transfer, and then closing a channel. So when either side wish to open a channel, it allocate a local number for the channel and then send a message on this channel. Okay, this diagram show the exchange of the messages. during connection protocol. So as we know that the life of connection consists of three phases: open a channel, data transfer, and close a channel. So when you are going to open a channel, the message that is being sent is SSH message open channel, and when channel has been open, it means a unique local number is assigned to this channel, and then message can be sent on the channel. So once it receives confirmation from the server, a channel has been opened between client and server, and then data can be transferred on this channel, and once data transfer finish, you need to close this channel through this message SSH message channel close. Okay, there are four type of recognized channel in SSH connection protocol specification, which are session, X11, forwarded TCP/IP, and directed TCP/IP. If it is session, it means the remote execution of a program. The program can be a shell or an application like file transfer or email or any system command. So once a session channel is open, subsequent requested are used to start the remote program. If channel type is X11, it refers to X window system, which is a computer software system and network protocol that provide graphical user interface for network computers. So X11 allow applications to run on a network server but to be displayed on a desktop machine. Okay, forwarded TCP/IP is remote port forwarding, and direct TCP/IP is local port forwarding. Okay, port forwarding is considered to be very useful feature of secure shell. What is the port forwarding? It provides the ability to convert any insecure TCP connection into a secure SSH connection. We also called it SSH tunneling, because TCP normal connection is insecure. So when we convert it into SSH connection, then it's called port forwarding. Okay, what is a port? Port is an ID of a user of TCP. Like whenever a TCP connection is established, a new socket is created, and this socket is assigned a unique ID. This ID is called port number. So each service is running, or each connection is established on a unique port number. And when a host receive a message on the network from the network, in order to find out to which program this message has to be delivered, it needs the appropriate port number for it. And well-known services are using well-known port number, like HTTP is using 80, port 80, FTP is using port 2021, SMTP is working on port 25. Okay, and it's not necessary that an application always use same port number or one port number. It can use multiple port numbers as well. Okay, this diagram shows the basic concept behind port forwarding. In normal TCP connection, when a TCP connection is established, client choose its own port on which client application is running, and here we assume that client application is running on port number X and server application is running on port number Y, and client send request to connect to the server application on port X. So the local TCP entity negotiate a TCP connection with the remote TCP entity, and then connection will link this local port. On client side we call it local port, and on server side it is remote port Y. So this connection is established from local port X to remote port Y. Okay, this is normal TCP connection. But when we want to secure this connection through SSH, then SSH is configured, so that SSH transport layer protocol. Now you know that SSH transport layer protocol will establish a TCP connection between the same client and server. So when SSH is invoked on top of it, you have unsecure connection already, and now we invoke SSH. When we invoke SSH, then SSH transport layer protocol also need to establish a TCP connection between same pair of client and server. So this TCP connection that SSH transport layer protocol will use it will use its own port on client side local port A with remote side remote port B. So SSH will establish a connection on local between a local port A and remote port B. So this is SSH TCP connection. So when traffic from the client at port X is redirected to the local SSH entity and will travel through this tunnel where the remote SSH entity will deliver the data to this server application on port Y. So traffic in the other direction, like from server to client, will also go through same way. With port forwarding, we can use a local port forwarding as well as remote port forwarding. Then there is dynamic port forwarding. There are different type of port forwarding options available with SSH. And here we finish our chapter where we cover all these topics. Thank you.